Okay, so let's start. So welcome everyone to the ICTS string seminar. And today we are very happy to have Aninda Sinha from ISC, who will tell us about causing symmetric dispersion relation in QFT and CFT. So please start.
Okay, so thank you very much. Thank you very much for the invitation. So hopefully I'm audible and there is no echo and my screen is visible to everybody.
Yes, you're audible.
I'm going to tell you about, yes. So I'm going to tell you about crossing symmetric dispersion relations in quantum field theory and conformal field theory. And don't get scared by the number of slides that I have on the right hand side. I don't think I'll have I'll have time to cover more than half of it. Here is an outline of my talk. So I'm going to start with a sort of a background as to what the problem we are studying, why it is interesting. It has got some history, so I have to give you some background before things start to make sense. So I'll give you a brief history of the crossing symmetric dispersion relation, and then I'll do some sanity checks that this new way of thinking about things works. Then I'll give you a derivation. Depending on time, we will go through the derivation slowly or fast. And then we'll come to the most interesting part, which is applications in quantum field theory, which will involve generalizations of the Froissart bound and connections with what is called the Bieberbach conjecture in mathematics. And then, depending on how much time I have, I will connect it with the Polyakov bootstrap in conformal field theory. And I should tell you that this last point, the Polyakov bootstrap was one of the main motivations for looking into this problem. And so whatever I'm going to discuss about the quantum field theory part has some generalization, has some overlap with the conformal field theory part. So let's begin with a brief history. So let's define the problem carefully. So let's consider 2-to-2 scattering of identical massive scalars. So there are some generalizations that one can consider. One can consider massless particles, which I'll talk about right at the end if there is interest. And if I don't mention massless particles and you're still interested, do ask me at the end. So when we consider a 2-to-2 scattering of identical massive scalars in perturbative quantum field theory, we use Feynman diagrams, and we know this from the first course in quantum field theory. And since we're considering identical massive scalars, this will have manifest crossing symmetry, means that if I permute ST and U, the amplitude will be invariant. Now, so this is a perturbative representation. A non-perturbative representation of the amplitude follows from usually, let's say usually, not generally, but it usually follows from what are called fixed T dispersion relations. So I will give a background on these dispersion relations in a bit. But once you fix one of these Mandelstam variables, you lose manifest crossing symmetry. And then you need to impose this as a constraint. So then the question becomes, where are the Feynman diagrams from this dispersion relation point of view? Now there's an analogous question, and this is what actually got us into thinking about this problem, that you can ask an analogous question in conformal field theory, and this was posed by Polyakov in 1974. He said that if we try to bootstrap a conformal field theory correlator, then it should look like, and this is our modern interpretation of what he was saying. He was saying that there is a version of the conformal field theory correlator, which we now understand as the Mellin transform. So this M here on the left-hand side is the Mellin transform of the conformal field theory correlator. And he was saying that it must be expandable in terms of what we would like to interpret as exchange Witten diagrams. So this is a basis, this is a kinematical basis. So there could be exchange Witten diagrams and potentially contact diagrams. So of course, he did not cast his conjecture in this language. He cast it in terms of things that are no longer familiar. It's very difficult to connect it up with this language. This was our interpretation. And this is something that I've been working with Rajesh, Apratim, Kallol, and we wrote a few papers. I've been working on this problem for the last 5 years. This was the main motivation, that if we are given an amplitude, then can there exist a crossing symmetric basis? Now, when I say it in this language, you would begin to wonder that if it is already crossing symmetric, then where are the constraints going to come from? And that's a very important question. So keep that in mind. So this is based on a few papers that we've written over the last few months. So the first one was on the QFT side with my graduate student Ahmadullah Zahid, who should be there in the audience, and which is going to appear in physical review letters. And then there's a follow-up work with Rajesh and Ahmadullah on the conformal field theory side, which basically gives a non-perturbative derivation of the Polyakov bootstrap. And there's a more recent work, which I wrote with Parthiv, who's my graduate student in ISC, and Ahmadullah as well, which connects up with the Bieberbach conjecture, which I feel is a very exciting connection, which I hope I'll be able to cover. And there's a whole bunch of ongoing work with Prashant Raman, who's a postdoc in ISC, and Ahmadullah and Parthiv in disjoint union of these collaborators. So let me begin with some basics. And I would encourage that you unmute yourself and let's have discussions as the talk goes on, because very quickly things might become a bit too technical. So without discussions, it might be hard to follow. So this is a very quick overview about dispersion relations. So imagine that you have a function of one variable f of z, and you know that the structure is such that there is a cut along the real axis, and you also know that it has got nice properties which basically enables you to close the contour at infinity. So if this function did not have these nice properties, you would require to make something called subtractions, but in principle it's always possible. Then you write down using Cauchy's theorem an integral of this kind, which gets related using Cauchy's theorem to the discontinuity across the cut. So instead of a contour integral, you get a line integral starting from the cut to infinity. So the point is that there is some high energy input. So where does scattering come in? So f of z is just a function. Soon you will see that we will relate this to a dispersion relation for scattering amplitude. And basically there is an implicit high energy input. You require the arcs to die, otherwise you wouldn't be able to complete the integral. You would require to justify, I wouldn't say assume, but you require to justify that the arcs can be dropped. So the structure on the complex Z plane could be that there are these threshold cuts, but there could also be poles corresponding to stable massive exchanges, and also potentially a pole at 0, which corresponds to a massless exchange. But for simplicity and most of the talk, I will discuss situations where these kind of poles are absent. So once you have a dispersion relation, what do you do? So you start off with a 2-to-2 scattering amplitude. S and T are the usual Mandelstam invariants. You can decompose this in what is called a partial wave expansion. So these PLs here are Legendre polynomials. So if you're in 4 dimensions, they will be the Legendre polynomials. This combination of the Mandelstam invariants here is cos of theta. So theta is the angle that the incoming and outgoing particles make in the center of mass frame. F subscript L is the partial wave amplitude. And there is a generalization of this in arbitrary dimensions where PL gets replaced by the Gegenbaur polynomials. So, but just to have things concrete and in terms of things that are familiar, let's just focus on the case that is 4 dimensional. So once you have these partial wave expansion, you also know that for unitary theories, there will be partial wave unitarity bounds, which will give a restriction on these f of L's, which is given in this box. So this was for the full amplitude. You can also talk about the amplitude, the discontinuity of the amplitude across the cut, which is called the absorptive part. So it has a similar expansion, except that instead of these partial wave amplitudes, you pick up the imaginary part or the discontinuous part of the partial wave amplitude. So the imaginary part I will call A subscript L, A for absorptive. So that is why it is we use this notation. And so basically, what is the game that we want to play? We want to start off with the dispersion relation. We want to have a decomposition of this kind. And then using unitarity, which will put restrictions on these partial wave amplitudes, and also some mathematical properties of these Legendre polynomials or Gegenbaur polynomials, we want to make statements about the positivity of the amplitude or the absorptive part of the amplitude and find restrictions on the low energy expansion of this amplitude. So is the background clear? So
hello.
Yes, Loga, yes.
And so why is, like, I'm just a bit confused. You're saying mod FL square is less than imaginary part of FL? Shouldn't it be the other way around?
No, so the optical theorem is going to tell you that.
Okay, mod FL square.
Yeah.
Okay.
Yeah.
You're not saying mod FL. Okay.
Yes.
Aninda.
Yes.
Hi. So can we state this unitarity conditions as a modulus of 1 plus FL should be less than 1, should less than equal to 1?
Yeah. So there is something like that. You can recast it in terms of what you just now said. Yeah.
Because
yeah.
1 would be the one that gives you delta function, right? I mean,
yes.
one part of the S matrix, and then unitarity of the S matrix should mean 1
indeed.
plus
you can rewrite it like
modulus
that
of that.
well. Indeed. Okay. Yeah. I will prefer using this part, which is the absorptive part, because that is the part that is going to enter the dispersion relation. And so all that I will focus on is the fact that these ALs are positive. So that is where unitarity is going to enter my game.
I see. So you will use the upper bound or the lower bound on the imaginary part of FL?
I will not use this part. I will only use this part.
Yeah. Okay, thank you.
Yeah. Most of the time. So there are some testing grounds. I will make it clear what I'm using when. Okay, so what is the fixed T dispersion relation? So this is a 2-to-2 scattering expansion. So what is a fixed T dispersion relation? So what you do is that you know that in the complex S plane there will be these threshold cuts. These are the normal threshold cuts. I'm ignoring the case where there could be anomalous thresholds, where the threshold cut starts at 4m squared. This follows from the optical theorem. And what we do is, so M is a function of SNT. So in order to use Cauchy's theorem, we need to consider a single variable case. So what is usually done is T is held fixed, and then one writes down an integral over S prime. So S prime is the integration variable, which is like S. And usually there is the S channel cut, but because of this constraint that S plus T plus U is 4m squared, you'll also have the U channel cut on the left hand side. And this gap is kind of important because otherwise you will not be able to analytically continue from here to there. So what we usually do is we write down a dispersion relation for the amplitude, which takes on the form that I wrote down here for f of z. So it looks quite similar, and it takes on this form. So here, of course, as you know, if you have identical scalar massive particles scattering, then you should have a crossing symmetry. So what is usually done is that you impose crossing as a constraint at the next level. So this representation here does not have crossing. You impose it as a constraint. Now, I should point out, this is an aside. You can ask me later on to amplify on this, but you can just, you could have asked that, okay, if I start off with a representation like this, why can't I just take 1/3 of the cyclically permuted amplitude and just sum them up and say that that is the amplitude? And the reason is that you want to impose a partial wave expansion, and the partial wave expansion does not converge except inside a Mandel-Stan triangle. So you won't be able to do that, basically. That's the short answer. So this is the background, which I just wanted to tell you very quickly so that I don't lose you, because soon I will introduce another kind of dispersion relation, which is going to manifest the full crossing symmetry. So let me just pause here and ask if there are any questions regarding this background before I explain the big picture. Okay, so let me explain to you what the big picture here is. Because as I was telling you that it might get a bit technical and I don't want to lose you. So the big picture is the following. So here, as I told you, this does not have manifest crossing symmetry. So it's hard to imagine how Feynman diagrams emerge on the right-hand side. So what we are going to do is we're going to write down a parametric manifestly crossing symmetric dispersion relation. So instead of working with the standard Mandelstam variables, we're going to make a change of variables to a variable called z, which will play a very important role, and another parameter called a, which I'm going to hold fixed, like the case where we hold t fixed when we write down a fixed t dispersion relation. Here we will write down a dispersion relation in terms of this new variable. I will explain and I will define this variable very carefully as time goes on. But basically, this is going to be a parameter which we are going to hold fixed and write down a dispersion relation in this variable z. So what is this new variable that I'm talking about? So it's basically a change of coordinates which takes you from the complex S plane to a complex Z plane, such that these cuts here get mapped to arcs on the boundary of a unit disk. And it is possible, I will show you explicit transformation where this happens, just to sort of go ahead of myself. What is this A and what is this Z? So A is basically the ratio of the cubic Mandelstam invariant. So if you're doing 2-to-2 scattering of identical scalar particles or identical particles, this amplitude can be expanded in terms of a cubic invariant, which is STU, or a quadratic invariant, which is the sum of ST, SU, and UT. So this cubic invariant is what I'm going to call Y throughout my talk, and this quadratic invariant is what I'm going to call X. So just to make sure that you remember that Y, whenever you see Y, it's a cubic invariant. Whenever you see X, it's a quadratic invariant. And this variable Z that I'm going to introduce, I will explain a bit more a little bit later, is related to these invariants in this funny way. So basically Y over X, we are holding fixed. And there is this Z is going to come about. I will explain why it is Z cubed and so on. How did we come up with this? But basically, just to make you familiar with what my Z variable is, let me just say that X is related to A and Z through this relation, and Y is related to A and Z through this relation. It's a very, very important relation. It's Z cubed over Z cubed minus 1 square. Just make a mental note of this formula, because when I connect it up with the Bieberbach conjecture, this formula is going to be very important. Okay. The thing is that the big picture is that we are going to write down manifestly crossing symmetric dispersion relation, which is going to tell us.
Anindu,
Yes,
can I
yes,
start?
Yes.
So so you're mapping the branch cuts onto the boundary of the disk.
Yes.
So is the upper half plane mapped to the interior by these maps, or?
Yes. So the upper half plane, in fact, the lower half plane as well. And there are regions which get mapped to the interior. So once I give you the explicit formula, we will see how things get mapped.
Okay. Okay.
Just to bear with me for a little bit.
Okay.
Yeah. Yes. Yeah, I have a more explicit discussion about this change of coordinates in a bit. Yeah. So the idea is that we're going to write down a dispersion relation, which is manifestly crossing symmetric, so that we don't have to solve these crossing symmetric constraints to get sort of the optimum bounds. So once we have this manifestly crossing symmetric dispersion relation, we can ask, or we can study positivity in a more efficient manner, so to speak. And you will see that there is more mileage to be gained through this representation.
Sorry, Aninda,
yes.
Maybe you will comment on this, but in recent papers by Karen Ho, Rastelli, and friends, and so on, where they put constraints on Wilson coefficients, does crossing symmetric play any role there, or
yes, I will tell you. Yeah, it plays a very important role. I will tell you exactly what role it plays.
Yeah, thanks.
Indeed, it's a very good question. Just ask me if in case I forget to tell you, Abhijit, please ask me again. What is the relation? Yeah, but indeed. So the game that we're going to play now is that, so imagine that I have this 2-to-2 scattering amplitude. I can always do an expansion of this kind. You can think of this as a low energy effective expansion. So typically in any scattering experiments, we will just focus on the lower order terms. But as string theorists, we pretend that we know a lot more, and we will also focus on higher order terms and so on. But these coefficients here are what are called Wilson coefficients, like what Abhijit just now said. So if I drop to the jargons, calling something Wilson coefficients, this is what they are. So this was the sort of the quantum field theory big picture, but there is a big picture, or there is a very interesting picture, let's put it that way, so far as mathematics is concerned as well, which makes use of a formalism in mathematics, which has been studied for more than 100 years now, which is called univalence. Now, we know typically that if you have a complex file, if you have an analytic function and you know something about, say, for example, in the context of dispersion relation, you know that the arcs at infinity die off, you know that that information, which is basically information about high energy, is actually powerful to constrain low energy physics. So that is where this whole thing is relevant. I mean, we are making some mild input about the high energy behavior, and we are getting constraints on the low energy physics. There is yet another such property which is less explored, less well known, which is called univalence. So univalence is the following. So suppose you have a function, an analytic function inside the unit disk, and univalence means the following, that this function is equal to so f of z1 is equal to f of z2, and this is only if z1 is equal to z2. So in mathematical parlance, this is sometimes called injective. So that this is what it means, univalence. And why is this powerful? So let me consider a simple example, and this is very instructive. Suppose we consider a function like this. So in mentally, you can think of this truncated functions as low energy effective expansion in terms of derivatives, and we have truncated to a particular order. If you want to think about it in a physics language. So f of z, suppose it is z plus a times z squared. So I've just normalized the coefficient in front of the linear term to 1. And we are inside the unit disk, so mod of z is less than 1. So it's important that we are inside the unit disk. So whatever is happening on the boundary, we don't care about right now. So suppose f of z1 was equal to f of z2. So this is a calculation that you can immediately do. You can rewrite this equation, f of z1 is equal to f of z2, like so. Now you have to do a couple of clever things, which are not immediately obvious. First, you have to use what is called the reverse triangle inequality. So this reverse triangle inequality gives us a greater than equal to for the modulus of this complex number. Next, you use the triangle inequality. So you get 1 minus mod of this, and the whole thing is under mod sign. And the triangle inequality is going to give you an inequality so far as this is concerned. The triangle inequality is something less than equal to, and the reverse triangle inequality is something greater than equal to. So you get this constraint, which essentially gives you a restriction as to how big the modulus of A can be. So this is where the power of univalence comes in. So ordinarily or naively, you would have thought that, this is an analytic function, A can be as big as anything. But then if you tell me this extra information that this is univalent, then there is restrictions on A. And this is what is going to translate into two-sided bounds on the Wilson coefficients. And why is it two-sided? Because this is the absolute value. So if you have a real number, then this, if A is real, then this actually translates into A lying between -12 and 1/2. So this is a very simple example of where the power of univalence lies, and we will make use of more powerful theorems in a bit.
So in specifying, in saying something is univalent, specifying the domain of the function is important, right? So here it's this.
It is.
So this conclusion follows from the univalence of this function when z is in the disk.
Yes. Yes, indeed. It has to be inside the disk. And then, of course, we have to know that the function is univalent. So just to get ahead of myself, what is going to happen is that I will require to know that the kernel of the dispersion relation is univalent. And then that is going to be enough to give me some powerful bounds on the Wilson coefficient. Okay. Yeah. Okay, so this is the big picture. Now, okay, you will say that, fine, you're talking things that are not very familiar to us. What are you going to test it against? How do you know that whatever you're talking about is correct? So there are two things I'm going to test it against. Well, there are basically three things. The first thing is going to be Treelevel string theory, which I'm going to think of as an effective field theory. So this is so M is related to 2-to-2 scattering of dilitons in superstring theory, in type 2 superstring theory. So this has got an infinite number of poles. To be very, very specific, there is a kinematic prefactor that I'm removing, and removing this kinematic prefactor is going to be important. So this kinematic prefactor is an 8-derivative prefactor. If you want to think of it, this is the linearization of the famous R⁴ term in type 2 string theory. And whatever I've defined as curly M here times this kinematic prefactor is the full Treelevel 2-to-2 dileton scattering amplitude. So I will focus on this version of the scattering amplitude, where I have done one very important thing. I have multiplied by some factor here, which basically gets rid of the graviton pole. Either you get rid of this graviton pole this way, or you just subtract it out like so, and I will work with this subtracted graviton pole subtracted amplitude. Now you will wonder that why are you doing this? How do you know that this resulting theory is a sensible theory, or the fact that you're taking out this kinematic prefactor, you've subtracted out the graviton pole. So how do you know that the positivity of these absorptive part of the partial waves will hold? It does hold. You can actually do a check that if you compute these ALs for this amplitude, redefined amplitude, then the coefficients are indeed positive. And this is all that we will need so far as deriving bounds are concerned. In fact, we can do it using an arbitrary Gegenbauer polynomials in terms of arbitrary Gegenbauer polynomials. And in the language of space-time dimensions, you can do this nice exercise. It's usually not shown to us, but then you can show that AL, the way that I defined it, is actually positive for dimensions that are less than 24. So that's one testing ground. The other testing ground is going to be with the S-matrix bootstrap. So the S-matrix bootstrap is basically describing pion scattering. So this was a famous.
Sorry, Aninda.
Yes, yes.
Just kind of a tangential question. So just mathematically speaking about the Gegenbauer polynomials, is there something that's something that is special about Gegenbauer polynomials in dimension less than 24 or whatever? With alpha.
So far as just Gegenbauer polynomials is concerned, there is nothing special, because these guys are known to be positive whenever x is bigger than 1. So physically, x is like cos theta. So cos theta is between -1 and 1. But of course, we analytically continue and we consider situations where x is bigger than 1. And that is where the positivity of the Gegenbauer polynomials enters.
Right, and that's true for any value of
any dimensions, yes.
But there is no speciality that one could state which distinguishes d less than 24 and greater than 24.
No, not at the level of the Gegenbauer polynomials.
Okay,
not that
just at the level of these dual coefficients.
Yeah,
okay,
yeah. So this S-matrix bootstrap is a numerical thing where we constrain pion scattering, but using only unitarity, so to speak. So we put in very little. So we put in unitarity, which is the strongest form of the unitarity, not just AL bigger than 0, but we actually use mod of FL squared less than 1. And we can convert that into a semi-definite programming problem. And this was done by a lot of people. It basically builds on whatever Paulos, Penedones, Van Vries, and Vieira did. And I should say that these numerics, what I'm showing here, were done on the ICTS cluster. I'm very grateful for ICTS for lending me that cluster. So let me just explain what this diagram means. So on the x-axis, we have what is called a spin 0 Adler 0. So Adler zeros are basically parameters, special values of the Mandelstam variable s, which and these special zeros come because of there being an approximate symmetry in the problem, which I don't have time to explain. But basically, you can think of S0 and S2 as two parameters. We dial them and ask, in this space, what are the consistent S matrices which are allowed by unitarity? And one very important extra phenomenological input, which is I'm going to put in the value of the rho meson mass. So this is literally a sort of a theory. One of these S matrices in the allowed region could potentially describe nature. So what we do is we now impose various constraints because, of course, to reduce the allowed number of S matrices down, you require to put in more constraints. So here in getting these so-called river boundaries, we impose some additional SP and D wave inequalities, which are just basically motivated from chiral perturbation theory. So you can ask me later on where this came from, but for now, you just think that we have put in some more constraint. The most interesting, there are two very interesting lines in this plot. One of them is this Lovelace-Shapiro line of models, which was a precursor to modern string theory. And then there is another line here, this one, which is the line of minimum total scattering cross-section. So in getting this minimum line, I have just used the rho meson mass and unitarity. What is striking, at least at the level of this plot, is the chiral perturbation theory, which is marked by red cross, the intersection of the Lovelace-Shapiro model and this minimum line of models which allow minimum total scattering cross-section all seem to intersect at a very interesting region, which is close to where chiral perturbation theory lives. So basically, the way that what I'm going to think about so far as this plot is concerned, I have got this enormous number of interesting S matrices, basically in principle, a continuous family along this boundary, a continuous family along this boundary, and here as well. And I'm going to test whatever I want using these S matrices. So that is what essentially what I'm going to do so far as this S matrix bootstrap S matrices are concerned. There's also some interesting story that I don't have time to go into, but if ND Haridas is there in the audience, he has been asking me. So basically, there are interesting regions where you have emergent linearity in the rigid trajectories, and this is one of the regions. Okay, so the other thing that we are going to test it against is one loop 5 to the 4th theory that you can just open Crespin and Schroeder, take the amplitude and put it to test. Okay, so this was basically getting the background, getting the sort of the test beds, what we are going to test our theories against. So let's now finally get going. So what is this crossing symmetric dispersion relation? This actually builds on a relatively unknown paper that was written in 1972 by Oberson and Khoury. So I don't know if there is anybody in the audience who knew Oberson and Khoury. But this is from the point of view of mathematical physics, this is a very, very nice paper. The only drawback of this paper is that the most useful formula that was there in this paper was in a note added. So if you go through the formulas in the main text, none of the formulas are going to seem useful or familiar to you. But there is a very, very important formula which was specified in a note added. Here also there is a TIFR connection, because crossing symmetric dispersion relation was also worked on by SM Roy and his collaborators in the 1970s. I believe that this did not catch on because I think the main use of these crossing symmetric dispersion relations is in the context of effective field theories, and probably that was the reason why this never caught on. So let me just tell you what the formula is, and then I'll put it to test. So S1 and S2 are the analogs of the Mandelstam invariance. This is the amplitude. So S1 is just a shifted version of the Mandelstam variable. So I've just shifted it such that S1 plus S2 plus S3 is equal to 0. And one of the reasons why I want to do that is if I wanted to consider massless scattering, I could easily do that. So even for a massless theory, S1 plus S2 plus S3 would be equal to 0 rather than 4m squared. So what does this crossing symmetric dispersion relation look like? So it looks like there is an integral, which is usually what you're going to see even when you write down fixed T dispersion relations. So this here, the lower limit is just a version of 4m squared in the shifted variables. There is an absorptive part, and the absorptive part is very interesting. The absorptive part ordinarily would be just a function of the integration variable and T, and which T would be what you would put here and you would hold fixed. And so it looks like an absorptive, this is the absorptive part. Instead of T, we see this funny function S2 plus. S2 plus will remind you of a solution to a quadratic equation. I will tell you where exactly this comes from in a bit. Times of kernel. Yes.
So here it is assumed that there is no subtraction needed.
No, here I will, in fact, indeed, I will use twice subtracted dispersion relations to write this. So if you had no subtractions, then these factors S1, S2, S3 would be missing here.
Okay. So here the assumption is that M dies in the region limit as S is
yeah. So
yeah,
the precise statement is that it goes like little o s squared. So it is like operationally it is like s to the power 2 minus epsilon.
Yeah. Okay. Thank you.
Yeah. Okay. So why are we saying that this is crossing symmetric? So crossing symmetric means that if I look at the formula, then I should immediately be able to see cyclic symmetry in permuting ST and U or S1, S2, S3. So here is a kernel. Kernel is obviously crossing symmetric because if I cyclically permute S1, S2, S3, this guy is invariant. The only other place where S1, S2, S3 enters, and it's a very important place, is through this A dependence of this S2 plus. So A was the ratio of the cubic to the quadratic invariant. Now this obviously is manifestly crossing symmetric. So if I decided to examine the S1, S2, S3 dependence of this entire representation, it is manifestly crossing symmetric. Now, you would say, okay, you've shown me this representation. How do you know that this is correct? So let's go to the string theory question and try to answer the following. So I have given you this amplitude. You can think of this as a mathematical question, that it's a product of gamma functions, it's a ratio of gamma functions. Can I expand this in terms of residue or residue of the poles that are there in S1, S2, and S1 plus S2? So S3 is, because of this constraint that S plus T plus U is 4m squared, satisfies this restriction here. So that is what why there are poles even in this variable. And the question is, can we just expand it and write it as something over S1 minus something plus something over S2 minus something plus something over S1 plus S2 minus something? So can there be such a representation? So you could do this first exercise, and this is doomed to fail. So you would first try to do you would just naively just sum over the residues. This does not work. This is a very useful exercise. In fact, anybody who's already getting bored with this talk, you just open Mathematica, copy this function down, and try to see if you can write this as a sum over poles. But if you did the other thing, which actually follows from the dispersion relation intuition, if you just summed over the S and U channel poles, then this works. And this works because of the fact that there is actually a dispersion relation which makes this symmetry manifest, the SU interchange symmetry manifest, which is the fixed D dispersion relation. So the non-trivial question that I'm asking here is there a representation of this kind for the amplitude? So what is the representation I'm looking for? I want to sum over all the poles. Potentially, I want to add contact terms. These are going to be basically polynomials in an S1, S2, S3. So these are like exchanges. This is like a contact diagram. And times it could be dressed by a non-trivial crossing symmetric function. And this is where the difference arises. Now, if you open Green-Schwarz-Witten and you read chapter 1, you're taught that your string theory amplitude, if you sum over S channel poles, is going to reproduce what is the sum over T channel poles. Now, if I flashed an answer of this kind, you would have thought that, oh, if I now extrapolate to what I learned from Green-Schwarz-Witten, am I overcounting? I'm not overcounting for a very important reason, because there is this dressing factor here, which is not simply the residue. It's a more complicated function, which is a function of X and Y. So that is if in case you were just trying to extrapolate to what you learned in string theory, that is the explanation why it is not contradicting anything that you know in string theory.
Sorry, what did you say? So this is not just a function of T, but rather it's some complicated function
exactly.
of X and Y.
Yes, yes. So what does this, so if I plugged in this answer, because I know the answer, so I can just work out the absorptive part. If I just plugged it in, what would the representation look like? So this, I'm just telling you that there is a manifestly crossing symmetric sort of an expansion, which should begin to remind you of exchange diagrams. And basically, this dressing factor that I made a song and dance about just now, this is basically a product of gamma functions in some sort of suggestive manner. I don't know what this representation actually means, if there's something deeper than what I'm just showing you here. But there's an important thing. The important thing is that these guys, these gamma functions, if you just take them, so they are non-trivial functions of this variable A. A was just ratio of y divided by x, and that is a very important thing. So if you expanded this around a equal to 0, you would start seeing higher and higher order polynomials in y over x. And keep that in mind. It will play a very important role in a bit. So I have given you this function. There's a sum from 0 to infinity. And you could just say that, OK, I know the left-hand side, so let's compare. So here I give you a comparison where the agreement between the left-hand side, which is the exact answer, and the right-hand side where I've truncated up to some, say, 100 terms or something. And I'm just asking where in the real S1, S2 plane is there 10% agreement. And there's a large region where there's a very good agreement between the two representations. For comparison, I've also shown here the two-channel dispersion relation. So the light blue and the green is where the two-channel dispersion relation works. And the deep blue and the light blue is where the crossing symmetric dispersion relation works, meaning that it gives you a good answer within 10% of the exact answer. And you can repeat this exercise also for the 2D Ising Mellin amplitude, in case anybody is familiar with Mellin representation of CFT correlators. And there is an equally good thing there as well.
Sorry, Aninda.
Yes.
The nice thing about the usual dispersion relation is that unitarity, is a very nice, you can just state it in a very nice way. Where is the unitarity in this expression? What is something is supposed to be positive here?
Yeah, so that's a good question.
Positive,
I will address this. So here we are going to expand this absorptive part again using the usual partial wave expansion. So the usual partial wave expansion looks like each term in the expansion looks like AL as a function of S1, or here S1 prime, times the Gegenbar polynomial, which is basically a function of this S2 plus. Okay, so AL is still going to be positive. It is going to be between 0 and 1 when I do the partial wave decomposition of the absorptive part. Okay. Now, the nonlinear part of the unitarity, which is mod of FL squared less than 1, that becomes more complicated in this language, but in principle, it can be done. So, but whatever I'm talking about right now, we are just going to be interested in putting AL bigger than 0. Is that okay, Abhijit?
Sorry, Aninda. This A function here, this is a function of only one variable, small a, right?
No, so this absorptive part is a function of the integration variable S1 prime. So when I write a partial wave decomposition of this guy, I'm going to write this as some 2L plus 1 or whatever, and then there'll be S1 prime, and then here I will write the Legendre polynomials, and then 1 plus, and here I'm going to write 2S2 plus divided by S1 prime minus A. S1 prime.
I see. S2 plus is somehow treated as T.
Yes, exactly.
And S1 prime is treated as, and the S1 prime minus 4m squared also or not?
Yeah, no. So in my language,
there's
some version, there's some shifted version.
I see. Yeah. Okay. I see. And then this you will show why this is the right meaning. This is the right implication of unitarity, right?
Yeah. So I mean, I'm going to use that this is once I do a partial wave decomposition, unitarity is just a statement that ALs are bigger than 0 and bounded by 1. And also there is this nonlinear version where FL square is less than 1. So when I'm going to derive these bounds, or when I'm going to talk about the Bieberbach conjecture, I will just require that these ALs are positive.
No, but does it follow from the standard unitarity that once written in this crossing symmetric way that this must be the case?
Yes.
Is it obvious? Or?
Yes. Because so far as the absorptive part is concerned, I'm doing nothing. I'm just using the usual decomposition. So the absorptive part has got nothing to do with the dispersion relation.
I see.
Yeah.
Okay.
So when we write this kind of a partial wave expansion,
I see. I see. Okay. Thank you.
Yeah. So there are all kinds of checks that you can do. You can put in complex values as well, and you can see that the exact and this representation works very nicely. But there is an important part. So I told you that there are going to be these higher and higher powers of y over x. So just let's imagine that we have fixed any one term in k. We have fixed k and we are looking at this ratio of gamma functions and we are expanding around equal to 0. So what you're going to find is that you will get an infinite number of powers of a in this particular term. So, and that's peculiar because you're going to get an infinite number of negative powers of x. What was x? X was just a quadratic invariant. So it was like st plus su plus tu. So that was x. If I look at the left-hand side, this is my exact answer, I know it. I will see no such negative powers of x. So in order to have this crossing symmetric representation, I have had to pay a penalty. So in each of these basis vectors, so each term in K I'm calling a basis vector, I've had to use some spurious singularities. Spurious non-local singularities, I'm calling them non-local because of the negative power of x. So in an effective field theory, I shouldn't be seeing negative powers of x in the 2-to-2 scattering expansion. So that is why I call them non-local singularities. So this is just a summary of what I just now said, that in order to write down a crossing symmetric dispersion relation, I've had to pay a penalty. And that's a good penalty because you will see that in order to get equivalence between the physics of the fixed T dispersion relation and the crossing symmetric dispersion relation, you require to have this. So the statement is that once we sum over all Ks, these negative powers will cancel. These negative powers, a priori negative powers that we have introduced in a basis vector will cancel. So just to emphasize, to have a crossing symmetric expansion, it seems that we have to introduce spurious or non-local singularities to the basis elements. And just to the experts who have encountered this before, I should just point out that these non-local singularities have got nothing to do with the Polyakov double poles. And later on, I will tell you what that means in case anybody is interested. Okay, so that was the sanity check that this representation works. So are there any questions so far as the sanity check is concerned? And because I'm now going to tell you a bit quickly about the derivation of the crossing symmetric dispersion.
So hello?
Yeah, Loga, yeah. Yes, Loga, tell me.
So I'm just, so the statement is that the object that you had as the coefficient when you're expanding the Treelevel string amplitude as a function of A.
Yeah.
So it has a Taylor expansion in E. Is that the point?
Yes.
Yes. Zero plus corrections.
Yes.
And you want to cancel all the positive powers of A.
Negative powers of x. Negative powers of x. So we don't have to cancel all positive powers because there could be some x to the power m, and we could have y to the power y by x to the power n, something like this. And then we want to cancel only those terms where we have negative powers of x.
Okay. Right.
Yeah.
But where will the y come from? Because this whole thing is only a function of A, right?
Yeah, so A is y over x. So I should have said that. So A is y over x. So A here is
so
y
the whole expansion is just expansion in y over x, right?
Yes.
Wouldn't every term in this expansion have the same power of y and x? It won't have.
No, because you see, so here this is also a function of x and y. So so this is some function of x and y, and so we will expand this, and then that is where I'm going to get positive powers of x. It's a good question. Well, thank you, because it shows that you're paying attention.
Okay. You're saying so you're going to expand that also, and that will give you some separate x's and y's, not y over x.
Yes.
And then after that, you are going to cancel all the negative powers of x.
That's right.
Okay.
And Aninda, this equation can be produced just using this formula that you have, right?
Yes.
The way to obtain this is by and there you consider discontinuity to be delta functions and so on.
Yes, exactly.
Okay.
That's right. Yes. So Loga, is that clear? Was that clear?
Yes.
Thank you. Okay, so let me give you a quick derivation of the crossing symmetric dispersion relation. I'm very sorry that already it might seem a little technical, but that is what it is. So the derivation of the crossing symmetric dispersion relation can be found in this original paper by Robertson and Curry themselves. But there are some minor typos, inconsequential typos in the derivation, and some obviously because of the fact that they had a compact paper, steps were missing. So if you want to see the steps, you can find it in the supplementary material of our paper. Okay, so now this variable is familiar to you. It is just A is y by x. And so I'm giving you this parametric dispersion relation, and I'm also telling you that S1 plus S2 plus S3 is equal to 0. And I'm asking, can I find an explicit parameterization of this constraint, because this is a constraint. So how do we go about doing that? And this can be done in case of situations where you have two channel symmetry as well. So for instance, suppose you you have open string, where instead of R to the 4, you have S to the 4, and then there is something that is symmetric on the ST interchange. You can do the same thing with some differences. And I'll be happy to talk about the differences later on. So you can actually sort of mentally see, if you're paying attention, you can just put this inside in your head, that this parameterization that I've written here solves these two equations. So what is this parameterization? So I have A here. So A is a familiar A. This ZK here are the cube roots of unity. So Z1 is 1, ZK is omega, and Z2 is omega, and Z3 is omega square. And it is needed because 1 plus omega square is equal to 0. So you can actually see that if you plug this inside this equation here, this equation is satisfied. So this is the parameterization that we're looking for. So the next question is, what does the original complex S-plane look like in this new variable Z that we've introduced? Okay. And this looks very nice. It looks very nice for various reasons, but let me just tell you what it looks like. The cuts, there are cuts in 3 channels. So you have S channel cut, C channel cut, U channel cut. They get mapped to various portions of arcs on the boundary. So for example, the S channel cut gets mapped to this plus this. The U channel cut gets mapped to this and this and this and this, depending on what value of E I've chosen. So this figure that I'm showing you is for a range of values of A. And there are other reasons why this representation is very useful. So other reason is 2 things. One of them is that if you are interested in the low energy expansion, then that would actually correspond to being close to the origin. If you are interested in the Regge limit, this would mean you are going to these location of the cube roots of unity. So the Regge limit, for example, if you are taking S1 fixed and you're taking S2 and S3 to infinity, would correspond to taking Z to Z1 or Z to 1 in this language. So that's why this this complex Z plane is very, very useful. And you will see even a better use of this when I connect it up with the Bieberbach conjecture.
So what is the analytic structure in the A plane?
So A, of course, it's a great question. So this is something that we have not thought about in great detail, because we are keeping A fixed. In particular, whatever we are going to choose will require us to derive a range of A, where whatever statements we are making hold.
I see.
Yeah, but it's an important question to figure out what it looks like in A as well, which is something that we have not thought about. Yes. Okay, so I told you that there's this funny looking S2 plus which replaced T. Where did that come from? The answer is very simple, that this is a linear constraint, S1 plus S2 plus S3, and you just plug this constraint inside here, you'll get a quadratic equation for S2. So S2 plus is basically one of the roots for that quadratic equation. Because we have 3 channel crossing symmetry, the other root, whether we use this root or the other root does not make any difference. So we've made a choice and we are working with S2 plus. So that is where this S2 plus came about. So once we introduce these variables, the idea is very simple. You have to now you write down a fixed A dispersion relation in Z. So again, I'm flashing to you the representations of Y and X, these cubic invariants and quadratic invariants in terms of Z. And here I should just begin to introduce some more mathematics of the univalent functions. These functions, this Z cube over Z cube minus 1 square, are in the mathematics literature what are called Kobe functions. These are extremal functions so far as univalent functions is concerned. And the other thing that you should immediately note is that if I have a low energy expansion, it will be an expansion in polynomials in X and Y. That would also correspond to an expansion in Z cubed. So Z on its own never appears in the fully crossing symmetric case. It's only Z cubed. Okay. So when we write down a dispersion relation, we have to assume something about the high energy behavior. Otherwise, we wouldn't know whether we are allowed to close the contour or not. Now, in the fixed T dispersion,
Aninda? So this is So this is a Kobe function of Z cube, right? I mean, it's univalent in Z cube.
Yes.
I mean,
indeed.
it's kind of like repeated thrice, actually.
Yes.
Right? Like
Yes.
It's not.
That's right.
It's not
Very
quite
good.
injective. Yes. It's kind of.
Yes. So it is univalent in Z tilde, which is Z cube. You're right.
Okay.
Yes. Okay, so we have to say something about the high energy behavior. So you can do a lot of things. There is a formal way of deriving this as well in the fixed T dispersion relation, which basically first needs you to assume that there is some S1 to the power n behavior, and then you need to derive what is called the Froissart bound, and then use something called the Fragment-Lindelof theorem, which puts a bound on n. So that is the chain where this behavior is derived in the fixed T dispersion relation. For the purpose of this talk, we will just assume that this is true.
So one question, Aninda. The crossing symmetry would imply that the stuff should be only function of Z cube, right?
Yes.
But that is the cyclic symmetry only. But there is a Z2 permutation also, right? Which is part of crossing.
Yes. So you mean that that is the analog of S1 S2 interchange?
Yeah, S1 S2 flip. Yeah. And
that,
so, how does it?
Yeah. So that's a good question. So in the language of X and Y, so another thing that I think what happens is that these are also invariant under Z going to 1 over Z.
Mm-hmm.
Yeah, so that probably has to do with this this permutation exchange that you're talking about. I'm not 100% sure. Let me think about that. Yeah.
You probably want to like have a complex conjugate, right? Like because you have an origin will get mapped to infinity. You want to kind of preserve this. I don't know.
Yeah.
So, but I think like.
I think you want something like this.
Yeah. I think you just want to make this. You want if you also include complex conjugation, then I think basically omega square if flip.
Okay. Yeah, that's a good point. Yes.
Like then I think it would be.
Yes. Yeah, I think you're right. Yes. These are good questions. So they don't play a role in what I'm going to say, but then they might play a role later on. Let's see. Okay. So the idea is that once you make an assumption for the falloff, you want to write down an integral, which basically enables you to close outside the disk and close inside the disk. So that's basically what the game that we're going to play now. So we write down a circuit which is outside the disk and another circuit which is inside the disk, and basically take the difference of the two. So that's the idea, and you can just use Cauchy's theorem, and you convert it back to the S1 variable. You'll get the form that I showed you, that I played around with, which I did some sanity checks to show that it works. Okay. Now I went through this derivation very quickly, but in case I'm pretty sure Loga followed everything. So in case anybody has questions, maybe I should take a 5-second breather and ask if there are questions regarding at least in principles. I did not show you any algebra, but then in principle, do you have any questions? Okay. I just want maybe I should make a note of this, that it turns out that when you do this calculation carefully, that this is just the value of the amplitude at S1 equal to 0 and S2 equal to 0. This constant that we cannot fix. So whenever we make subtractions, there are constants that we introduce in the representation which we cannot fix, and so this is one of the constants. This is like in 5 to the 4th theory, this is like lambda. This is what defines the coupling constant.
So what is the behavior of M in the Z variable near origin and near the near infinity?
So M is regular, so it has a Taylor series expansion around Z equal to 0. And so if you look at the variables S1, so around infinity, if you take Z to infinity, then S1 and S2 and S3 all go to 0.
I see. So it's this, inversion kind of thing.
Yeah, inversion kind of thing, exactly.
Okay.
Okay, so now what is the game that we play next? The game that we play next has to do with knowing that this is positive. So we need to plug in the partial wave expansion and use unitarity. So this will be positive. And then we need some mathematical properties of these Gegenbauer polynomials. So I told you that if the argument of the Gegenbauer polynomial is bigger than 1, then this is a mathematical property that the Gegenbauers are positive. So this is not true if you're in the physical regime, which means x is less than 1 or between -1 and 1. So one advantage of having a crossing symmetric dispersion relation is that you can write down straight away formulas. If you want to call them inversion formulas, you can call them inversion formulas. You can write down straight away formulas for these Wilson coefficients in terms of the absorptive part, which means that in terms of these ALs, and times some things that we know. So these are some linear combination of derivatives of Gegenbauer polynomials. And in fact, later on, we realize that this can be written in terms of what is called a Jacobi polynomial as well. But now we are in a position to play a game. So we know that these are positive and these do not have any definite signs, but we know what these functions are, and we can try to get linear combinations of these Wilson coefficients using these known properties of these objects here to show that this linear combination of these Wilson coefficients are positive. So that is one game that we can play. So that's indeed the way that one can derive a bound, and we can, in fact, we can write down a general set of bounds. In fact, there is such a general set of bounds written in our paper, and you can play all kinds of interesting games using those. So that's one game that we can play. So, but let's ask a more conceptual question. So in the beginning, I made a big hue and cry about where are the Feynman diagrams. Because in the usual dispersion relation, we do not see the structure of Feynman diagrams. By that, I mean that you need to see some exchanges, maybe some contact diagrams. Where is that structure emerging from this?
So one more question. So the massless exchanges are subtracted out, right? Have they? Or this works with massless?
Yeah, so massless exchanges here. So for example, the Treelevel dilaton scattering amplitude, I have, when I'm going to play around, I have subtracted off the massless exchange. I will tell you a bit about massless exchange right at the end. In fact, the massless exchange question is a very, very interesting question. What I believe is going to happen is that, at least in the story of this Bieberbach conjecture, you can add massless exchanges in the language of effective field theory. Because what you have to do is you'll have to work with a punctured disk. And there are stories about univalent functions in the punctured disk or even the annulus, which people have developed over the last 100 years.
I see.
Yeah. So let me just give you this conceptual answer that where is this structure? Because whatever I've shown you so far seems like it is very remotely connected with Feynman diagrams. We don't see Feynman diagrams emerging from this story. So where can we see this emerging? This is where this non-locality in non-locality in this X variable that I told you, which is sort of inbuilt into this formalism, plays a role. So let's start off by writing two different forms of the expansion of the amplitude. So one of them is just plugging in the absorptive part, which is just the expansion in terms of the Gegenbauer polynomial. This guy is what I would like to call, each term in this expansion is what is called Regge bounded. Why is it Regge bounded? Because if you look at the high energy limit, the only place where S1, S2, S3 sits explicitly is through the kernel and through A. And if you look at the kernel, it is like S1 over S1 minus S1 prime, or S1 over S1 minus sigma. So when I take the large variable limit, S1, S2, S3 limit, then this guy is bounded. And this is also bounded because A is bounded. So this is what I would like to call as Regge bounded. And I would like to give it a name because we have to call it something. Otherwise, we'll continuously refer to this as singularity block expansion with non-local singularities. And we will refer to this second one as block expansion without non-local singularities. So instead of using that nomenclature, let's call this Dyson block expansion.
Sorry, Aninda, when you say Regge bounded, it's in a given channel, right? I mean, in the T channel, it's still unbounded.
Yes. It's in the usual way that we take the Regge limit. So in that sense, it's Regge bounded. Because the kernel is Regge bounded regardless of how you take the limit. So in any channel, if you keep S1 fixed and take the S2, S3 going to infinity, then it's Regge bounded and so on. Is that clear?
So,
yeah.
And what was alpha here? What is this 2 alpha?
Oh, alpha was related to the dimension. So in 4 dimensions, alpha is half. And
Okay.
so it keeps increasing by 1. Yeah.
Okay.
Yeah. So you could have said that, okay, but you told me that there are these non-local singularities in this expansion. What would an expansion look like if I remove these non-local singularities? And it looks very, very nice. And it's very suggestive because this is exactly the kind of expansion that we have been looking for in the Mellin amplitude story, in the Witten diagram story that Rajesh and I and Apratim and Kollol and many others, including Amadullah, we have been fighting for, looking for, literally struggling to find for almost the last 5 years. If you remove these non-local singularities, this looks very suggestive. It looks like exchanges plus polynomials, and each of these polynomials we know explicitly. So it's not that we are adding some polynomials by hand, coefficients we do not know. These polynomials, these contact diagrams, we fix explicitly. So this kind of expansion, which at least each partial wave looks like an exchange plus a contact diagram, we should call the Feynman block expansion. And then you can do some sanity checks. You can ask that, okay, let's do a Dyson block expansion compared with the exact answer. And in fact, the convergence is extremely good. You just convert, you just keep 6 partial waves, 6 spin partial waves, and only a few terms in the poles. It converges very quickly. This is a fractional deviation, so it's a sub% agreement with the exact answer.
Sorry, Aninda, I think I'm confused.
Yes,
so in this page here where you write the Dyson block and Feynman block expansions, I was thinking that the first one is the usual partial wave expansion, and the second one is your crossing symmetric partial wave expansion.
Yes.
And in the second one,
this is also crossing symmetric. This is also crossing symmetric. Because the kernel is crossing symmetric, A is crossing symmetric because it's the ratio of y over x.
So I didn't quite understand the difference between the two, because I thought so far you talked about only one form of the crossing symmetric expansion.
Yeah.
And now you have 2 forms.
Yeah. So let me just explain a little bit more. So here we start off with this guy.
Yeah.
Okay. And here we are just and we write the partial wave expansion for this absorptive part. So it is that gives the Dyson block.
Okay.
That is what I'm calling the Dyson block expansion.
Okay.
I told you that if I do an expansion around a equal to 0, then there will be these negative powers in x.
Yes.
And there were these non-local constraints that we have to impose. Now, let me just go ahead because I am pretty sure that I won't reach that part of the story. That you see, so in the fixed T dispersion relation, what would we do? So we would write a fixed T dispersion relation. Now, the fixed T dispersion relation, if you just play around with it, you will know that the fixed T dispersion relation does not have any of these non-local terms. Right. Okay. So the fixed T dispersion relation is local, but we have to impose crossing symmetry. Okay.
Yeah.
Now, so that is the constraint that we get from the fixed T dispersion relation. Here, I'm saying that this is a manifestly crossing symmetric dispersion relation. Now, if that was the story, then we don't get any other extra constraints. Where are these constraints that are analogous to these crossing symmetry constraints that are imposed in the fixed T dispersion relation? Where are they coming from? And the statement is that we have to impose these non-locality. To remove these non-locality, we have to remove these negative powers of x. And that is the analog of these crossing symmetry constraints in the fixed T dispersion relation.
I see. Okay.
Okay. So we know that in a physical amplitude, a local amplitude, these negative powers of x are going to cancel. So here, all that I'm asking is that suppose I decided to expand in terms of a basis that had these non-local terms to remove from the start, because I know that on the spectrum, when I sum over all the partial waves, it's going to cancel. So I have to impose that constraint, the non-locality constraints, separately anyway. All I'm asking
but is it clear that this will happen block by block? It may happen that after summing all this, they may cancel.
Yeah. No. I'm not saying that this is happening block by block. So all that I'm doing is that I am saying that when I rewrite this, there is going to be a sum over L times some negative power of S. So suppose we are looking at a particular negative power of N. And suppose I'm looking at some positive power of N. And then there is some coefficient here, say Cn. Okay. So these will look like this. So there could be a power which looks like this. And the locality constraints tells us that this must be 0. Okay, so I have removed all these terms from the expansion. I'm not doing it block by block. So sorry if I give you the impression that I'm looking at a particular spin and I'm removing all the negative powers of x at that level.
Okay.
So all that I'm saying, so I'm saying that let's impose this. and see what the expansion after we impose this looks like. So what I'm saying, of course, I've skipped a lot of steps, and because of lack of time, I can't show you the steps. But what I'm saying is that when you do that, what you're left with is an expansion that looks like this, where all these polynomials are fixed.
I see. I see. Okay.
Yeah.
Thanks.
So you can now do sanity checks. You can compare. In fact, the Feynman block and Dyson block seem to do equally well. And then you could ask that, okay, you said that, okay, these contact terms are important. How do we know that they're important? So in fact, you can do that sanity check as well. You can compare the values of the exact. So this is exact known answer. So here is the Feynman block expansion. Here is the Dyson block expansion. And as you can see, it works very well. It compares very well with the exact known answer. And you could have said that, okay, let's remove the contact terms and do it. And you can start seeing that there are mismatches, important mismatches. For instance, here, this is 0.79 and here it is 0.33. So if you remove the contact terms, you're going to get some big mismatch. So the contact terms are indeed extremely important. Okay. So this is a proposed nomenclature. So basically the Feynman block in quantum field theory, the analog of that should be the Witten block expansion in the CFT, and the Dyson block, I believe, should be called the Polyakov block, which is Regge bounded, but it is manifestly crossing symmetric. Okay. Now I have to pace myself depending on how much time I have left. So if you can tell me how much time I have, I will go fast or slow.
You're 10 minutes past the time, but I guess you can take maybe 10, 15 minutes more. I don't know.
Okay, so then I will pace it accordingly. So there are a whole bunch of applications that we can do. So let me just keep the QFT applications. Basically, the kind of questions that you can ask is that you can write down these inequalities I just now told you by looking at the properties of this guy. And in fact, play a game with the string low energy effective expansion. So the question that here I'm asking is that suppose I give you some terms in the low energy effective expansion. Suppose I give you up till some order, maybe 10 derivative or 12 derivative order. Then does this expansion know where the first massive string state is? So of course, we know the answer from beforehand. We know that the first massive string state is going to be in my language at S1 equal to 1. But just by looking at this low energy effective expansion, do we know where the first massive string state is? In fact, you can use these inequalities, which follows from the crossing symmetric dispersion relation, and you see that it very quickly, within a few derivative order, it converges to the right answer. So in fact, at leading order itself, it is a very close agreement. It gives you a value of 1.08, where the known answer is 1. So that's just a very quick sort of display of where one can use this crossing symmetric constraints. So this is also a good place to actually answer Abhijit's question. So he was asking that Karen Huot and Andrew Tully and a company, they were writing down these, they've been looking at these bounds on the Wilson coefficients. So there are two kinds of bounds that people find. One of them is what looks like, say, if you're looking at the leading ratio of Wilson coefficients, they get a bound from this side and they get a bound from the other side. And this is called a two-sided bound. Now, depending on your conventions, one of them is actually going to rely on crossing symmetry. Without imposing crossing symmetry, you don't get the bound on one of these sides. Okay, Abhijit, did that answer your question? So in my conventions, this upper bound that I'm going to get relies on crossing symmetry.
Okay.
Okay. So this is what that answer is, that you really require to impose crossing symmetry to get these two-sided bounds. You can also find the extremal solution because we know the coefficients in these inequalities explicitly. And there's a story there I don't have time to go to.
Sorry, this was kind of interesting. So you're saying there's some extremization that you can do and get to string theory?
No, so I should have said, so here I was comparing with the string theory answer. So by comparison, what I meant is that you take the string theory answer and you compute these quantities here. These are just basically some normalized versions of the Wilson coefficients. And you look at the extremal solution to the inequalities.
Okay.
Makes these equal. And if you compare, you will see that, okay, so for the first level, there are some discrepancies. This is 1.5, this is 1.4, and so on. But as you go to higher levels, it very quickly starts agreeing. So in the sense that it agrees to 10 decimal place, and beyond that, Mathematica does not. I mean, of course, you can see the difference, but the difference happens at a very high decimal position. And the extremal solution in the original variables looks very simple. It is just where the first massive string state would have been located. Yeah. That is what you can derive from this exercise. Yeah. So I wanted to say that this is string theory for a different reason, because you asked me, let me just say that. So if we knew where the first massive string state is located, we could actually subtract it out. Like I subtracted out the first massive pole, first massless pole, the graviton pole, and I located where the first massive string state is. Now I subtracted out subtract out this massive first massive string state as well, and ask where is the second massive string state. I repeat this whole exercise using the crossing symmetric dispersion relation, and it gives you the value S2 equal to 2, which is the location of the second massive string state. So that is why I think it has some connection. Yeah. But this is the most interesting part. Let me just quickly tell you this connection with what is called the Bieberbach conjecture. So here is the connection with the Bieberbach conjecture. So I told you the power of univalence. The power of univalence was that if you have an expansion, a single variable complex function, which is analytic inside the unit disk, and which is univalent, that means that f of z1 is unequal to z2 if z1 is not equal to z2, then the modulus of these coefficients are bounded. Bieberbach in 1916 made a conjecture that the magnitude of these ans in this function should be less than or equal to n. So that is why it is called the Bieberbach conjecture. Now it was proved in complete generality for even complex ans by Desbranches in 1985. That is why it's now called the Desbranches theorem. My claim is that there is an analog of the left-hand side in quantum field theory. Very specifically, what we will show is that there are these two-sided bounds which follow from this inequality, which are basically you rewrite m in terms of z and a, you expand like so, and call the coefficients alpha n. Then the alpha n divided by alpha 1 will also be bounded exactly by n. And this I can derive using the crossing symmetric dispersion relation. So that is why there is this very interesting connection with the Bieberbach conjecture. And you could ask, so if you use this, I will go through the derivation because it just takes 4 lines. I will go through the derivation of this inequality in a bit, but you get a very strong bound. Why is it strong? Because it is dimension independent. This bound does not have anything to do with the space-time dimensions. Whereas the bound that Simon and Andrew Tolley had, this right-hand side would have been dimension dependent. Now, curiously, of course, Simon does a lot of extra interesting stuff in his paper. This number that I get here, that I quote here, coincides with whatever he has in the infinite dimension limit. So it has some connection, explicit connection with whatever they have done, but what I'm quoting here is definitely stronger than what they have. And then you can ask, okay, then how do you test it? I mean, maybe what I'm showing you is not correct, and maybe it gets violated for some known theories. So you can play around with the S-matrix bootstrap story, and you will see that it's nicely two-sided bounded exactly in the numbers, using the numbers that we have. So this guy is the upper bound, which does not have, this is the strongest that we know in the literature, which follows from this Bieberbach connection. And this is the lower bound, which coincides with whatever Tolley and Karenhoff have. And it does seem that there are S matrices which are trying to approach this upper bound. So in that sense, it is non-trivial. So there are a lot of interesting things that you can do, which I don't have time to go to. In particular, you can derive two-sided bounds on the magnitude of the amplitude itself. It follows from what is in the mathematics side of the literature is known as the Kobe distortion theorems. So they have a similar two-sided bound on the inequality, which basically is analogous to the S-square inequality. Now you would have said that, okay, but you use the fact that in order to derive the dispersion relation, you used S-square fall-off. But this bound is stronger because this is valid not just for large S, not just in the Regel limit, but more generally. So whatever the analog of this side is, whatever the analog of this side is obeyed more generally. And there are all kinds of parallels, interesting parallels between the two sides of the story. So there are these interesting things called the Gransky inequalities, which appear and which are necessary and sufficient for univalence. And then there is an interesting consequence of these Bransky inequalities, which gives you nonlinear inequalities on the Wilson coefficients. Okay, so let me quickly now run and show you a derivation. So I should also mention, in case you were interested, that a sufficient condition for proving univalence is by calculating the Schwartzian of the function. The Schwartzian is something that we do in conformal field theory all the time. And there's a very interesting story that the Schwartzian also plays. There is even more connection that one can find with the mathematics literature. So that is that on the quantum field theory side, we want to think in terms of effective field theory. So what is this analog of this effective field theory on in the univalent side? So indeed, there is such a story, and that goes using a connection with what is called the Segos theorem, which uses the partial sums for these Wilson coefficients. In my language, these are Wilson coefficients. So because of lack of time, I don't have time to go through this in any detail, but let me just tell you very interestingly. So this was the Z complex Z plane plot that I showed you. And I told you that in the fully crossing symmetric object, the correct variable is Z cubed, not Z. And so this is the plot in the complex Z cube plane. So Z tilde Z cubed. So all the S channel, T channel cut gets marked to this red arc on the boundary. This is the low energy region. This is the Regge high energy region. So geometrically, it looks quite pleasing. And the key point, this is what I should pause and tell you why this works, is because this kernel here is basically a univalent function. So once I do this integral, and this is the absorptive part of the amplitude, and I determine the conditions where the absorptive part is positive, then this is just telling me that the amplitude is the convex sum of univalent functions. And that is
sorry, Aninda.
Yes.
Just kind of a meta question. I mean, this kernel here, you know it explicitly what that function is.
Yes.
Not just that it is univalent, it is this particular function.
Yes, yeah, exactly.
Why is it important to call it a univalent function rather than to just specify, you know the function completely?
Yes, I know. But you see, what is going to happen is that I will require to know specific properties of the Taylor expansion coefficients of this function.
Yeah, but you just do the Taylor expansion and see the properties.
Yeah, so but that is very hard to study. Yeah, because
I mean, if you say some function is there which you don't know what it is, and you know that it is univalent, then you can impose abstract bounds without knowing any other information about the function. But here, you know the function, you can expand it, you can see it's 15, 16, and so whatever. So this is one thing that is a bit confusing to me. Why you emphasize on univalence rather than to just say, oh, see, you expand it and see the coefficients are all positive, and then that's what.
Yes, very good. Yeah. It's a great question. So there are two reasons why it is important. Because, so imagine that the Taylor expansion coefficients of this, let's call this beta n z to the power n something. Yeah, so beta n is a function of a. And so imagine that this is what it looks like, z tilde here. And I want to use this kind of an inequality. So I want to know, or I want to sort of, well, imagine that I tell you that numerically, I have played around and I have found that this is a function of A. So I have played around with A, and then I have found that, okay, so for some range of A, I have played around for n equal to 20, and I have found that this condition is. So this is the kind of test that you want to perform, right? Yes. Yeah. So you can definitely do that, except that it is not going to determine for you the exact range where this condition is going to hold.
Mm-hmm. Okay.
Okay. So but what I can do is I can study the properties of univalence of this function. This is the kernel. So this is just the kernel. This is kernel, just normalized in a certain way. This is the kernel. Yes. And I ask, where is this function univalent? So there are two observations that I make. One, this function is nothing but a Mobius transformation of the Kobe function. Okay. And two, if it is a Mobius transformation of the Kobe function, the only thing that I need to check is where are the singularities of this function. So I just need to make sure that in the unit disk, it is not singular. And that is what gives me a range of A. Is that clear, Abhijit?
Yes.
Yes. So using this, it's a literally four-line argument, which actually shows this two-sided bound on the Wilson coefficients, because this translates into two-sided bounds on Wilson coefficients. So basically, this is where I'm using this beta n is the Taylor expansion coefficient of this kernel. This is the formula. This is just follows from the dispersion relation, crossing symmetric dispersion relation. At level 1, I'm using triangle inequality. At level 2, I'm using the fact that A is positive for unitary theories. That is what enables me to pull this out. And then I'm left with the absolute value of beta n. And here, of course, there's a game. One has to verify the range of A where the absorptive part is positive, and this is the range of A. And at level 3, I use the Lagrange's theorem or the Univalence or whatever follows from the Bieberbach conjecture, the fact that beta n is less than n times beta 1. So this is the level where I use that. And then immediately I rewrite this in terms of alpha 1, and then this theorem follows. It's as easy as that. And you can study these inequalities more systematically. So I told you what the level 1 of the inequality gives us. It gives us this two-sided bound on the ratio of Wilson coefficients. And you can also play a lot of games. Yeah, tell me.
One question. Sorry, you have some range of A in which this is to be valid.
Yes.
And what does that translate into? Because these are now inequality on the Wilson coefficient.
Yes.
So
Wilson
where
coefficients
will
are not
the range of
yeah, so Wilson coefficients are not functions of A. Wilson coefficients are independent of A.
Right.
So this is precisely where the range of A where univalence holds translates into bounds on both sides. So in fact, if you recognize it, you see, so here it becomes 9/16. So on the ratio of this Wilson coefficient, on one side you see 9/8, on the other side you see 9/6.
I think. Okay, understood. Okay, thank you.
Yeah. And as I said that you can play a lot of games with these inequalities. It gives you the pretty tight ratio, which at least the S-matrix bootstrap seems to obey. And the upper limit, I don't know what this means. And Abhijit, you should tell me if you see any significance for this, that it coincides with whatever these people found in the d going to infinity limit. So maybe there's some simplification that happens in the d going to infinity limit. I don't know. Anyhow. But you can continue playing these games. So for example, suppose you can again ask that, suppose experimentally you know the Wilson coefficients up to some order, and then you did not know the next order Wilson coefficient. So what can you say about it? So imagine that you're doing this game with the string amplitude. Using this inequality, what you will find is that there is a very narrow range of allowed values. There's a very narrow range, and this black line here is where string theory sits. So what I've done here is that I've fed in the Wilson coefficients up to a certain order, and I'm asking, this is a 12 derivative Wilson coefficient, so what values can that take? So it does seem that it is tightly constrained. You can do the same thing for pion scattering as well, which is a more realistic problem to consider. Again, you play the same game, and again, you see that it is again tightly constrained, where the two-loop chiral perturbation theory value sits here, and the inequality gives us some range of values, which is not very big. That's it. So that is the main part of the story. And in fact, it gives you some very nice two-sided bounds, which you can verify using one loop 5 to the 4th theory if you want. Play around a lot. There are further things to play around with, basically using these other known inequalities, the necessary and sufficient conditions, which are called Bransky inequalities. And there's a lot of other things to play around with, which I believe I've not had time to explain, or some things are even not known to us, which I believe one can explore in the future. So I don't have time to explain any of this, this derivation of the Froissart bound and so on. Let me just quickly flash that using the same kind of philosophy, the same kind of crossing symmetric dispersion relation, you can provide a formal non-perturbative derivation of the Polyakov bootstrap. So this is the summary of what we have. On the left-hand side, the subscript P means that these are the constraints that comes from the fixed T dispersion relation. So this is the direct sum of crossing symmetry constraints and what comes from these Polyakov double pole conditions. And on the right-hand side, this is what comes from the crossing symmetry dispersion relation. They are equal. And they are equal. We have explicitly checked that we can recover these crossing symmetry constraints using whatever we have done. In fact, the equality only holds once we impose the locality constraints on the right-hand side or the crossing symmetry constraints on the left-hand side. And there are all kinds of checks that one can do using Mellin dispersion relations. So basically, to do a sanity check that we are not sort of saying something that can be easily ruled out using the fixed dispersion relation, things like that. But that is it. So basically, this is a non-perturbative derivation of the Witten block expansion. You can play a lot of games with analytic functionals as well, which I don't have time to explain. But these are my final comments, that I think crossing symmetric dispersion relations, at least in my mind, they're proving very handy and powerful. At least to derive these two-sided bounds, you have to impose crossing symmetry. There is no other way. In cases which do not have three-channel crossing symmetric, like what the open string amplitude that I mentioned, this is a work in progress with Prashant. And these are kind of things that you would like to ask in realistic, more realistic processes in QED, for example, molar scattering or Bava scattering, where you don't have this full three-channel crossing symmetry. You should be able to derive a similar story. And we have been able to, using this approach, place the Polyakov bootstrap from our footing. I think there are lots to do, and in fact, I don't think we have sort of I think we have just barely scratched the surface. There are a lot of creative things that are left to be done. So let me stop there and then open the floor for more questions.
Okay, thank you, Aninda, for the good talk. Are there any more questions for Aninda?
Hello, sir.
Yes.
Yes, sir. I have just one question, sir. Can you go to the slide number? Slide, I don't know, big picture, like math side and QFT side.
Math side and QFT side. So is this one? This one, is it? Yes.
Yeah. So here, this Bieberbach conjecture. So from this, using Bieberbach conjecture, we are getting in the QFT side that this quantity, like alpha n upon alpha 1, and this quantity less than equals to n.
Yeah.
Okay. So basically, there is one important point in the Bieberbach conjecture, that the equality holds only for the Kobe function and its rotation. So my question is that can we do such type of characterization in this QFT side also, like for what type of MZA, because this is the expansion of MZA. So what type of MZA will be there, so that this equality, such type of characterization is there?
It's a great question. So let me just break your question up into two steps. So the first thing is that when I derive the analog of these bounds, the two-sided bounds and the Wilson coefficients using the Bieberbach conjecture, what I was using is the univalence of the kernel. So I did not need to use the univalence of the full amplitude. Your question is at a very important level. You're asking, is the full amplitude univalent for some range of A, say? Okay, because this is a sum of univalent functions, and exactly. So in order to derive these bounds and the Wilson coefficients, I just needed the fact that the kernel, which is a part of this, the full representation, this was univalent. Now, your question is at a more difficult level, at a deeper level, is the full amplitude univalent somewhere? And what does that physically mean? Now, that I don't have anything clever to say, because there are no theorems, or there are no rigorous theorems that are known, at least right now. We are investigating this, which deals with the univalence of convex sum of univalent functions. So that, I think, is the thing to search for, that what exactly systematically can be said so far as the convex sum of univalent functions, so far as the full amplitude is concerned, whether we can say something more interesting about the full amplitude.
Okay.
So that is why I had to go through this very, very quickly. I said that I conjecture here, this is a conjecture, that univalence of the full amplitude holds around A equal to 0. And this is what we have tested for whatever theories that we have played around with. And that correlates with the Grunsky inequalities. The Grunsky inequalities are nonlinear inequalities. And that gives you this nonlinear inequality. And then you can go ahead and check whether this nonlinear inequality holds, and it does hold.
This is the Grunsky inequality. This is the Grunsky.
Yeah, exactly.
Yeah.
So the Grunsky inequality does hold. So, but of course, we have to prove from first principles that the full amplitude is univalent, at least as a Taylor series expansion around A equal to 0. So this is something that we have not done because we did not need it to derive the bounds that we have done so far. But I believe that if you want to play around with the full set of nonlinear inequalities, the Grunsky inequalities is for a infinite dimensional set of inequalities, very nonlinear.
So basically, you can choose as
yes,
your,
yes,
as per your choice.
yes, exactly.
Yeah.
So indeed. So yeah, Luca.
Okay, sir. Thank you, sir.
Yeah, yeah. So hope that answers that question.
Yeah, thank you, sir.
So good evening, sir.
Yeah.
This is Vasudev from IIT Bhubaneswar. Very nice
yes.
talk, and we work in the Univalence function theory.
Okay, okay. Hey.
So it's very nice talk. And sir, actually, I want to know as this Bieberbach conjecture was proved using these logarithmic coefficients.
Yes.
That
yes,
Univalence conjecture, where it contains the logarithmic bounds.
Yes.
So, is there any connection with this logarithmic coefficients and this quantum physics theory? This gamma n's?
Yeah, that's a great question. So I've been indeed thinking about it because I was proving the steps of proving the general Bieberbach conjecture. So I should say that whatever I've described so far is, strictly speaking, something that Rogozhinsky proved for the real coefficients long time back in 1931. But in the general proof of the Bieberbach conjecture, you use these Loener chains.
Yes.
And these Loener chains are very fascinating because they have an analog in conformal field theory. They have an analog in statistical physics. So, and indeed, let me just tell you. So, my amplitude is a function of two variables, Z and A. The Loener chain, you introduce an extra parameter which they introduce.
One parameter family.
Yes. I believe this A is related to this e to the power t. So you will be able to derive a Loener chain differential equation for this amplitude. And that will be very interesting to sort of understand what that means, because it seems to suggest that there is an auxiliary conformal field theory, two-dimensional conformal field theory role to be played here. So maybe this two-dimensional auxiliary conformal field theory has something to do with the string world sheet. So it will be a very fascinating game to sort of explore.
Yeah, here, but in the Bieberbach conjecture, we have even de Bruijn's theorem. We have modulus of n less than equals to n, whereas for the same class as we don't have a bound for gamma n for n greater than equals to 3.
Yes, yes.
So so we are wondering whether.
I'm not sure. Yeah, right, yeah.
So whether any connection between this gamma n's, at least in the summation form, like summation n equals to 1 to n modulus of gamma n square and something, has a connection with this quantum physics theory.
There could be. You're talking about the area theorem, basically. Is that right?
That is almost like an area theorem, but recent papers, like for example, Oliver Roth has written one paper in Proceedings of AMS. So there are some results containing instead of finding the individual gamma n's, there is a summation formula for which they can give an upper bound in the series form.
I see. No, I'm not looked at that, but the area theorem, I believe, might have some interesting physics interpretation in the language. I mean, if you try to recast all this, and there's a way to recast amplitudes, two-to-two scattering amplitudes in the language of quantum information theory. So it might have some bound, the amount of information that is bounded in the scattering amplitude. So maybe there is some physics interpretation.
Thank you very much.
Yeah.
I had a question.
Yes, I mean.
Hi, Aninda. Yeah. So, can you comment on the this crossing symmetric representation for the case of 2-to-2, the 2-to-2 scattering for massless particles? So whether for scalars or whether if you consider gluon or graviton scattering.
Yes. So, so there are two important things to keep in mind. So one of them is that there are these gaps. Let me not just for my diagram. But you require these gaps because you want to analytically continue your function from here to outside. Okay. Now, if you just naively did the arcs, so what happens in the complex S-plane? The arcs coincide, right? For the massless scattering, because the arcs start from S greater than equal to 4m square, and if m is 0, then it starts from S greater than equal to 0. So there is no gap between the left-hand cut and the right-hand cut.
Right.
So basically what happens in this picture is that there is no gap here. Okay. Now you can do a more restrictive case. And the restrictive case is that imagine that in the complex S plane, you have this following structure, that you have a massless particle here. And then you have maybe some more low energy states not continuous, but then some low energy states here. And then you know that there is some cut, some threshold cut, which definitely starts at some point. And some structure like this. Okay, suppose this was the structure that you're working with. Then in the Z variable, this has a very interesting representation. This basically gets mapped. So all this cut gets mapped to the boundary of the unit disk. So this gets mapped to the boundary of the unit disk. These low energy states get mapped to some region here. Okay, and so what you would like to do is say that you have analyticity in an annulus. So this is an annulus. And in fact, mathematicians have derived bounds, these Bieberbach type bounds, for univalent functions inside an annulus. So I believe that there is a way to connect up with if there are exchanges which are massless, or in this picture where you have some low energy states which get mapped to some region inside the disk.
Thank you.
Yes, Dr. Rao.
Tell me, Bashir.
Yes.
Okay, you are in the department or in the hostel?
Oh no, so I think he's not muted. Okay.
Okay, you can come. You can take the form. Okay.
Luca, please go ahead with your question.
Yeah. So Aninda, do you understand it right that that you're not using unitarity beyond some positivity of
Yes.
AL?
Correct.
Right. You're not
yes.
imposing some cutting rules or
Yes, that's right.
So I mean, what is the so there are no assumptions on what happens inside the disk, outside the disk, and so on. There can be extra branch cuts inside, outside, and so on. Is that right? That
yeah. So we are making an assumption about the what happens to the cuts in the complex S plane. Yeah. So that is definitely there because we are saying that the cuts get mapped to the boundary of the unit disk.
Okay.
So yeah. So
yes. Now. So, but those are all cut from the real axis, right?
Yes.
So the assumption is that there are no cuts outside the real axis.
Yes.
Okay, and
yes.
and that is known. Is that?
Yes. So the assumption that we're making in whatever story that I've told you so far, which is what we've done so far, is that the complex S plane, the structure is like this, and so there is some gap here. Okay, so this is an assumption. Now you could ask that in complete generality, I mean, could there be some other poles here, for example, for a bound state? So there could be poles here, and so I'm just assuming that you have the real axis poles are stable particles. There are cuts corresponding to the threshold bound states. I'm assuming that there are no anomalous thresholds. I don't know how to handle them. And that's about it. I mean, so whatever statements I just now made, where I said that you might have a univalence inside an annulus, I think this holds for this story.
Okay. So the point is that like if you just look at I'm trying to understand like how this mapping goes. So usually like when we think about like Kobe function and so on, it maps to almost everywhere in the complex plane except a slit.
Yes.
Okay.
Yes.
So the slit is where you're mapping the cut to. Is that
yeah, it's a so it's a little bit more complicated than that, because you see I was using the univalence of a disk of the kernel, and there is this gamma factor that is sitting here, which gets translated into some ratio of A and the integration variable. So this actually tells us what is the range of A, because S1 is bigger than some I forget, it's 2 mu by 3 or 8 by 3 in units where M is 1. That translates into the fact that mod of gamma here should be less than 2. So, so this is where univalence came in. So this is what gave us restrictions on the parameters. So A is a parameter. I'm holding that fixed. So that gives you a range of A where univalence holds. And then, yeah.
Okay.
Yeah.
Okay. Okay. And another question is that, like, so you said you were comparing it to also like 5/4 amplitudes.
Yes. One loop. Yes.
So the 5/4 of course has like it's a space of amplitudes with some the coupling lambda 5/4 lambda.
Yes.
So like so do you like what do you find, like because mainly you were talking about the string theory and chiral perturbation theory and so on. So
yeah, because we were working with one loop, the lambda that enters, I mean, because you have lambda and lambda square, and the cuts are in the lambda square term. So this lambda dependence cancels out in this ratio at the leading order that we are working in. So I think the kind of question that whether we can say something about a bound on lambda, which is what people in the ancient days in the 1970s they wanted to actually look at non-perturbative bounds on this coupling. That is going to show up only at the next order. So because we worked at one loop, it does not play a role. Did that answer your question?
Okay.
Yeah.
So you would say that you would say you would have to like put like the two loop diagrams.
Yes.
And then like you calculate some coefficients, then you might have some bounds on that.
Yes.
That
indeed.
Some
yes.
Okay.
Yes.
Okay.
Absolutely.
And the univalence, this A, I'm kind of surprised that A, where it is univalent, is kind of universal for all the theories. It doesn't depend on couplings and.
So yeah, so where it is, so the kernel is univalent. It's a very easy demonstration. So
you're saying this is kernel. Okay,
yeah.
Right.
So, yeah, exactly. So kernel actually is univalent whenever the mod of gamma is less than 2. So that translates into, so imagine you have a dispersion relation where your S1 integral starts at lambda. You can actually make a statement at that level itself. So suppose you're doing an effective field theory, where you're not starting from the cut, but you're thinking it in terms of some effective field theory language, so that there is a part of the amplitude that you know because you can do calculations, and then there's a part of the amplitude that you do not know. So you want to split your integral into two parts. So you want to start off at 4m square and then up to lambda, and then from lambda to infinity. So you can actually pull this known part to the left-hand side and redefine your Wilson coefficients as a function of lambda and make the same statement as a function of lambda. So this A over S, whatever I'm writing here, this will now become a function of lambda, this two sides of the bound. Did that make sense, Loga?
Okay. Yeah. Okay.
Yeah.
And one more question, then I'll stop. Okay. So I mean, so is there some simple relation to what you guys were doing with Mellin amplitudes and so on and so forth? I mean, like, is this story some flat space limit of some story in ADS? Like.
Yeah, indeed. In fact, there's a good relation to all this Bieberbach story. We have been investigating with Amadullah and Faizan. We have been investigating, and it seems like the 3D Ising model respects these bounds. So we are trying to sort of put that on firmer footing. So whether we can use these bounds to say something more interesting than for the 3D Ising model. So at that level, I think there's a very nice connection. So far as the general story, the general philosophy of crossing symmetric dispersion relation and the connection with whatever we were doing with Rajesh before this, yeah, indeed. So there is almost an immediate map. So this is something that I went through extremely quickly, where you can write down a dispersion relation for the Mellin amplitude itself. So you can write down, so this is what we are calling the Mellin amplitude. You can write down a dispersion relation for this Mellin amplitude. So instead of expanding in terms of the Gegenbauer polynomials, you now expand in terms of the Mach polynomials. Now, for reasons that are mathematically not completely well understood, the positivity property of the Gegenbauer polynomials still appear to hold for the Mach polynomials. And this cannot be shown completely generally in a mathematical sense, but you can do case-by-case study the way that Abhijit was asking, that why don't you just look at, you know the exact function, so why don't you just look at it numerically? And so you can do that game. And you can actually extrapolate whatever we just now saw about these two-sided bounds to the conformal field theory side. In fact, it does appear to work for whatever you have checks we have done so far. But this is something that we are still developing, so I don't know what the final outcome was, what the final sharp statement I can make for you is. Yeah.
Okay.
Any other questions?
I have one question.
Siddharth, yes.
Hi. So I just wanted to know when do these inequalities saturate?
That's very good. Very good. So I can show you one side. Okay. So I said that there are two sides of the inequalities. One is the upper side and one is the lower side. So in some language. So
Right.
I know the answer. I know the answer for the upper side. So this is what I very quickly say. So I can derive these kind of inequalities using these positivity properties of the Gegenbauer polynomials. This gives us a set of inequalities like this. These chi's here, I know a recursion relation. So in principle, I can compute any of these chi's. I don't know a general form of the chi's. I think the general form of the chi is some complicated hypergeometric function. But in principle, I can do to any order that I want. So I can get these inequalities for any n and any m. So n and m are given. So I get this chain of inequalities for any n and m. And then I set instead of inequality, I look at this condition, which is an equality. This I can easily solve on Mathematica. And these values on the first line in each of these tables are the solutions to these inequalities. Okay. Now, then I make one extra assumption. So one extra assumption is that you see, I have had to solve these W tildes, I know explicit solution as a ratio. So I have to make an assumption about one of these Wilson coefficients. So when I make that assumption, I can actually resum. So I do some black magic using this function in Mathematica called find sequence function. It tells me what these Wilson coefficients are in terms of x and y. So these x and y's are literally the x and y that I introduced earlier. And I can do that sum. And I get this. And when I rewrite it in terms of the S1, S2 variables, I get this very simple form, which is the first exchange pole in units where m is 1, or in the units where alpha prime is 1. So here it's better to call it the first massive string pole.
I see.
Yeah.
I see. So
yeah. So
you think it's saturated in some sense by having all these massive states in sync.
Yeah, that is what I would like to say, of course. But of course, the extremal solution that I found gives you one pole.
Right.
But then, of course, you would say that, okay, let's remove this pole, rewrite a dispersion relation, and find the extremal solution for that.
Right.
Then you will probably get something that looks very similar to this, but instead of 1, you will see 2, and so on. So maybe there is something to.
I see.
Like
Interesting.
That. Yeah.
Interesting. Okay, thanks.
Yeah.
And can you also say maybe a little bit more about you were saying there is some connection to EFT because you could prove in some you were saying that some analyticity property you could prove, right, in some disk, but you didn't really say it in detail because I think you were short of time, but you had this connection with EFT towards the end that you were
yes. Okay. No, I know what you're saying. So basically, so what is the structure? So let me just say two comments on the structure of the. Where's the disk? Where is the structure of the disk? Yes, here. So in the Z tilde plane, so this is the infrared, this is the low energy limit, and this is the high energy limit. Now, ordinarily, of course, we have very little information about what is going on at high energy. We don't know the amplitude at high energy. So what you want to do is you want to make a statement that is valid in some sense in a truncated expansion. You don't have to go all the way from here to there, but basically you want to restrict to some power of n. Because if you knew all the powers, so suppose you knew all the powers from n, and you knew all the powers from n equal to 1 to infinity, basically you know the whole thing, the whole amplitude inside the disk. But that is not what we do. And a more useful way to think about this would be if I could make statements about this. So where I have truncated, so I have not gone all the way to infinity, but I've truncated to some n. And the question then is that what can I say about this series? So the question that we can easily ask or easily address using known results in the mathematics literature is that does this series come from a univalent function? And what enables us to address this question is what is called the Sego's theorem. I had Sego's theorem somewhere. Yeah, here, this is Sego's theorem. So this is a condition on the partial sums. So I think in the review of mathematics literature, I quickly flashed Sego's theorem. So this is a check that you can do on partial sums of this kind. Okay. And these are conditions. These are necessary conditions on the nth partial sum of this function f, such that this function is a descendant of a univalent function. So this is the check. So this is the theorem that you have to check whether this nth section of this function remains univalent inside a unit disk. This you can do. So there are sufficient conditions that you can check, having to do with the derivative of the function not being zero anywhere inside the disk. And indeed,
Nice.
At least for string theory, you can show that indeed, as expected, it does respect this Sego's theorem criteria, that it is descended from a univalent function. So this is the plot that I did not have time to show you, but the similar plot also exists, for example, for whatever, I mean, even for say the S-matrix bootstrap, but this is a plot for the string theory case. So this is the lowest limit. The black dashed line is the lowest limit. So none of these zeta min, which is the location of the first, basically there's a root to a particular equation, and all these roots should be outside the quarter disk. And the minimum radius is indeed 0.25, which is what is given by Sego's theorem. So that is why there is some. I believe that there is a physical connection with effective field theories in this sense.
I see.
Yeah, Aninda,
thank you.
Can I ask one question?
Yes.
So, how things will change if I basically now start including the massless fields, particularly this conjecture?
Yes, extremely good question. I mean, this is what we are trying to investigate, and in fact, there are thankfully known theorems in the mathematics literature. So, where is this picture that I just now drew? So I had a picture here. So here I said that imagine that your structure in the complex S plane is like this, where you have some cut, which corresponds to some threshold cut, and then there are some bound state. And maybe one of the bound state is a massless exchange, which corresponds to having some pole at the origin. Okay. So the statement is that, so suppose, let's imagine that we only have the massless exchange. And I will qualify the statement a bit more. Then what happens is that this massless exchange gets mapped to the origin of the disk. Okay. This you can easily check using the fact that explicit formula for A and so on. I mean, you can check that the massless pole gets mapped to the origin of the disk. So the theorems that we want to use are theorems in the punctured disk. Okay. And there are mathematics theorems bounding these coefficients of these functions, these kind of Schlicht functions, are in the punctured disk as well. So that is what I would imagine is going to be the statement for just massless exchange. More generally, you might think that the structure is not like this. In fact, there are stable particles which correspond to maybe some region. Stable particles, of course, in nature, we know that we don't have arbitrarily massive stable particles. So maybe there's some region within which the stable particles lie.
Okay.
Then that would translate into the fact that there is some annulus within which the function is supposed to be univalent. And mathematicians have studied bounds on such functions as well. So in fact, there are interesting statements to be made there. Did that answer your question, Abhishek?
Yeah, thanks.
Any other questions?
Any last question for Aninda?
Yes. I guess.
Okay, if not, I guess we can thank you again for the great talk.
Thank you very much.
And I end the meeting now.
Yeah.
So bye.
Bye.
Bye.